Welcome to today's lecture. In the last lecture, we considered matrix operations and in particular used inverting a matrix to find the best fitting curve for a given set of data points. So, this as well as other things we will consider in the practical session after this class. Today I am going to do two more new items. One is we will discuss random numbers today. Look at the slide, fitting polynomials to a set of data points we studied in the last class. Also obtaining the roots of equation using Newton-Raphson method, this also we considered in the last class. Today we will do random numbers, integrals using Simpson's rule and differential equation. As I have been telling many times, our emphasis has been to introduce you to all these numerical methods. We are not going to be comprehensive. You just have to be comfortable with all the concepts and how to use very simple programs to do what you need. So, today we will be discussing random numbers. These are extremely useful in doing computer simulations such as the Monte Carlo simulation as well as calculating integrals which cannot be calculated in any other way. So, the next slide shows what I mean by random numbers. So, look at this slide. So, when we play cards, we know that there are 52 cards and each time you draw a card, it is completely random. Any one of the 52 can come and there is no formula to tell you which card will come when you pick one at random. Similarly, when you toss a coin, you can never predict whether it is head or tail, but when you toss it say a million times, you expect half the time it to be head and half the time it to be tail. Same thing when you throw dice, there are 6 options. So, on the average you will get each face 1/6 of the time. So, now this is conceptual, but I want to use a computer to get a set of random numbers. So, I shall illustrate it with a particular sequence. Look at this sequence, start with number 01. To this number 01, I multiply by number 13. So, the first result will be 13. I started with 1, my next result is 13. In the next step, I will multiply this 13 by 13. So, when I multiply 13 by 13, the answer is 169. Out of the 169, I will remove 100. So, what remains is 69. So, look at the following sequence. First number was 1, next number was 13, 13 into 13 was 169. Out of that 169, I removed 100. So, I got 69. Multiply 69 by 13 again, keep only the digits between 1 and 99. Okay. So, that is called a mod operation. Modulus operation is you divide a number by that 100 and only keep the remainder. It is a remainder operation. So, I got 97, then multiply 97 by 13 and remove all the multiples of 100, what remains is 61. Again multiply by 13, you get last 2 digits 93, and if you keep on repeating, I start with 1, it spans through all different numbers between 1 and 100, and again after 77 I come back to 01. Once I come back to 01 and multiply by 13, I will again get 13, 69, 97 and so on. So, after this 01, the entire sequence will repeat. So, in the range of this sequence, we got all numbers between 1 and 100. You see, there is a number between 10 and 20, there is a number between 60 and 70, there is a number between 90 and 100, there is a number between 0 and 10, there is a number between 20, 30. So, it is spanning my entire range in a more or less a uniform manner. So, these are called uniform random numbers. So, this is a very elementary algorithm. So, the next slide shows a more compact algorithm. So, what this algorithm says, a random number I is obtained by old random number, this was Ri minus 1, multiply that by some number, in our case it was 13. If you want, you can add or subtract something, then modulus m. Modulus m is the remainder function. In our earlier case, I used Ri is equal to 13 times Ri minus 1 plus 0, I did not add anything, mod 100, this is a modulus function. So, this particular algorithm, which I call them uniform random numbers because they are distributed between in this case it was between 0 and 100, I can always scale it between 0 and 1 by dividing by 100. So, they are uniformly distributed in a given range. These are uniform random numbers. A better algorithm will be, look at this, Ri will be 25173 Ri minus 1 plus 13849 modulus of 65536. So, you use this a large enough number, so that all my random numbers will lie between 1 and 65535. They will all lie between 1 and 65535. So, this is the better algorithm than the algorithm we considered here. So, now what I want to use? I want to use a professional algorithm to obtain a large number of random numbers, then we will see what to do with those random numbers. So, what I am going to use? I am going to have an algorithm for generating uniform random numbers. That particular algorithm we will not discuss in great detail, because it is a little more complicated than our normal things that we considered earlier. So, this particular algorithm I got from this numerical recipes in Fortran by W.S. Press et al. There are 4 authors. It is a very well known book, Numerical Recipes in Fortran. There is an Indian edition. So, this book has algorithms to solve many problems that you need in day to day analysis of chemical problems. So, it is a very well known book. These numerical recipes are there in Fortran, they are there in C, they are in other languages also. Okay. So, you may be able to download all the algorithms from the websites. The actual algorithms may be available on the website. So, for our today's program, we will use the uniform random number given in this book. So, I will just give you an outline of how to use those random numbers. So, I shall call this program random, that is the name of the program. I have given a dimension, distribution 100, 101. So, what I want to do? I want to generate random numbers between 0 and 1, and as you go along we will see what this 101 will do for us. So, idum, this is a variable to start this random number program. I have to give you a starting number idum, make sure it is not 0, because if it is 0 it will create a problem. So, in that book several algorithms are given for uniform random numbers. I am going to use the first one. So, this is my starting, it is called a seed. Then since I had 101 values of distr variable, I will assign all those to 0. So, this do loop do 50 I going from 101 to 101, 50 distri is equal to 0. So, all the values of this variable are adjusted to 0, are set to 0 at the beginning. Now, is my main loop, this do 100 I going from 1 to 10,000. So, this is my do loop. So, that is the statement up to 100, all the lines up to line 100 continue are repeated 10,000 times. So, what I want to do is to I want to get 10,000 random numbers, then arrange them in a particular way. Okay. So, do 100 I going from 1 to 10,000. So, A is equal to RAN0 IDUM. Okay. So, this is a function, this is a function RAN0 into bracket IDUM. I already defined IDUM once. So, it calls this random number function and the value of the random number is given as A. So, if we want we can write all those random numbers in some file, but it will be a very long file because there are 10,000 numbers in that. So, which we do not want to do that, it is a comment card. And once I have this random number, this random number A will lie between 0 and 1. So, what I want to do with this program, I want to know how many numbers are between 0 and 0.01, how many between 0 and 0.02. So, I want to make 100 boxes. I want to make 100 boxes, each of space 0.01, and I want to know how many random numbers will fall into each of the box. For example, suppose that random number was 0.5. So, what this is doing, m is equal to, this is 0.5 divided by 0.01. So, that will be 50 and I add 1. So, from that 0.5 I got a number 51, that m will be 51. So, the 51st box will be incremented by that 1. So, next time let us say my random number is 0.4. that 0.4 divided by 0.01 is 40, 40 plus 1 is 41. The 41st box will be incremented by 1. So, this way if I generate 10,000 random numbers and my range is between 0 and 1. So, if they are completely uniformly distributed, each bin of 0.01 size should have 100 random numbers. There should be 100 between 0 and 0.1, 100 between 0.01 and 0.02. So, each one of these bins should contain 100 numbers. So, we will see through the program whether each one will contain 100. So, if each of the bins contain 100, it will be a absolutely perfect random number between 0 and 1, but in general that does not happen. In fact, if it is too perfect, it is not probably as good. So, we will see the results in a later situation. Again, in this do loop, what I have done? I have obtained 10,000 random numbers, each is between 0 and 1, and to find out in which part of 0 and 1 it is, I am dividing by 0.01. So, when I divide that by 0.01, I get an integer between 1 and 100. So, each random number will be put in one of those bins, and my dist 100 will contain this distribution of random numbers. Okay. So, after this whole thing is over, it will write in file 11 distribution of random numbers, okay, and it will write all that array. DISTR is an array now, array of 101 points. So, when I say write 11 comma 101 DISTR, it will write all the 101 values of that array in file 11. File 11 here I have not given. If nothing is given, it will create some file by itself, okay, 4.11 FORT.11. It will create a file FORT.11, but you can always open unit equal to 11 some file name, you can do that as well. So, in this case it will create a file by itself. So, now all I have to show you is how this particular function works. The next slide shows details of this function. This function ran0idum, this is a function. That function uses several integer variables, it uses real variables, it uses many parameters, okay, and it does all these operations, and every time it returns you a random number. It returns you a random number which will be called in our earlier program it was a equal to ran0idum. Each time it gives you a random number as well as a new value of idum, okay, idum. So, you note this program, execute exactly what it is using gfortran, and we will not discuss too much about this because there are many professional algorithms which gives you random numbers. I have already discussed a very simple algorithm for you, and you know what random numbers are. So, once I do this, now I will consider another set of random numbers. Our earlier set of random numbers were uniformly distributed between 0 and 1. Now, this is a different distribution. These are called Gaussian random numbers. These are distributed between some minus value to plus value. The range is quite wide, but they are all peaked around that mean. They are peaked around a mean, and this is the standard deviation. These are called Gaussian random numbers. I shall also tell you the algorithm to get this. Okay. You can study that in great detail. I will give you the algorithm to get Gaussian random numbers. What are Gaussian random numbers? Now, they are distributed between minus infinity to infinity, because this x can take any value, but it is all peaked around 0 with a standard deviation of sigma. Okay. So, this py dy is a Gaussian random number distribution. So, it will be distributed as 1 by 2 pi e to the minus y square dy, sigma is equal to 1, mu is equal to 0. So, the way to do it would be you define two uniform random numbers y1 and y2, and from y1 and y2 you get x1 and x2. How do I get x1 and x2 from y1 and y2? x1 will be e to the minus half y1 square plus y2 square, this is 1, and x2 is 1 by 2 pi tan inverse y2 by y1. This arithmetic you can work out. So, all you have to do is to generate two random numbers y1 and y2 between 0 and 1, and from that generate two Gaussian random numbers x1 and x2. My next slide will give you greater picture of what this y1 and y2 are. So, look at this. Suppose I have two random numbers y1 and y2, and these random numbers both are between 0 and 1. So, y1 lies between 0 and 1, y2 lies between 0 and 1. So, since both are lying between 0 and 1, in principle this r square, which is the sum of y1 square and y2 square. So, in principle this r square can be 2, because y1 could be 1 and y2 could be 1. So, r square could be 1 square plus 1 square, that is 2 square. So, if r square is 2, that means the number will lie somewhere in that box. It will lie in a square box of edge length 2. Okay. But I want r square to be inside that circle. How do I ensure that r square to be inside the circle? When the sum of y1 square and y2 square is less than 1, then surely r square is less than 1. So, what I will do? I will get two random numbers y1 and y2. If the square of the two random numbers is less than 1, then only I will consider my remaining operations. So, only when r square is less than 1, I will proceed further. So, what are these y1 and y2? This is my y1, this is my y2. So, x1, I already told you how to get x1 in the previous slide, and how do you get x2? This angle is 2 pi x2. Okay. So, cos 2 pi x2 is y1 by r. Trigonometry will tell you that y1 by r is cos 2 pi x2, and y2 by r is sin 2 pi x2. So, this way I generate two Gaussian random numbers x1 and x2. Okay. So, its distribution is shown here. So, how is x1 distributed? By using the previous algorithm, it is distributed such that all values are allowed between a large negative value and a large positive value, and the random numbers are distributed which are peaked around x equal to 0. It is sharply peaked at the origin and with a standard deviation also 1. Okay. So, this is a distribution of x1. Okay. So, now this slide and the next slide gives you an algorithm to generate these Gaussian random numbers. Okay. So, all I have done here, just as in the earlier case, I define a new array 201. Now, if I want very accurate results, I need to use what is called double precision arithmetic. I have discussed it in one of the earlier classes. So, double precision arithmetic uses more spaces than the single precision arithmetic. Okay. So, I am not using higher precision here, I just am using a normal precision. Again idem equal to 1, 2, 3, I open two files 11 and 12. Okay. And I set all my a values to 0, do 5, I going from 1 to 201, I equal to 0, 5 continue. It sets all the initial values of my array a to be 0. Then is my next point, do 10 I going from 1 to 5000. It calls this Gaussian random number program 5000 times. So, I generate 5000 Gaussian random numbers by calling this function 5000 times. So, call gran, gran1, gran2, n count idem. Idem was my initial value, and as I mentioned before, do not ever set this initial value to be 0, then there will be a problem. Always it should be non-zero. Instead of 1, 2, 3, it could be 2, 3, 1, it could be something else, but never 0. So, I call my Gaussian random number function many times. It is a subroutine, I call it many times. So, once I call that Gaussian random number, now again I want to put that random number in some array, because we know that this Gaussian random number is going to be anywhere from some large negative value to large positive value. So, I want to put them in an array. So, when I put them in an array, so gran into 10, suppose that Gaussian random number is 0.5. If it is 0.5, that 0.5 into 10 is 50, okay. 50 plus 100 is 150. So, if the Gaussian random number is 0.5, this II will be 0.5. If the Gaussian random number is 0.1, 0.1 into 10 is 1 plus 100. So, it will be 101. So, this way wherever the Gaussian random number lies between a minus value and a plus value, I get an integer corresponding to that and I update my array II. I update my array A. So, if that random number comes many times, so that array will have values of that index. So, I will execute it and show you, but it may so happen that my array had only a size of 200. So, if this II is greater than 200 or if II is less than 0, it will not be able to accommodate in this array A. So, therefore, I just want to skip that, because if by chance the II becomes 202, it will give an error because A has a size of only 201, and if II is less than 0 or 0, again there is a problem. Okay. So, it will not accept. II will never be 0, because even if the random number is 0, whatever happens to that random number, that I am okay. So, if II is in principle, if II is 0, it could give you some trouble, but I can say, so to avoid that I can say II less than 1 instead of 0. If I make II less than 1, it will still execute. So, it ensures that II lies between 0 and 1 and 200. So, I will also execute and show you this program. So, then after I calculate all my random numbers, in this case there are 5000, it will write it in that file 12. Okay. So, this is the rest of the Gaussian random number function. This is the rest of the Gaussian random number function, and this also needs ran 0. Ran 0 was the uniform random number. So, that is also shown here. Ran 0 is exactly what was before. So, I will not show you ran 0 again. So, my program consists of okay. So, this is calling this is the subroutine gran. It calls ran 0. Ran 0 I have already explained. You add all the lines for ran 0 function in this program. So, the result of these two programs are as such. When I obtained a uniform random number, remember first program was uniform random number. See, it is uniformly distributed in some range. Whatever is the range, it is uniformly distributed, although it shows lot of fluctuations. These fluctuations really are not too much, because this is 100, 105, 110, 120. So, since I had generated 10,000 random numbers, each box had to contain 100. That there should be 100 random numbers between 0 and 0.01, 100 between 0.01 and 0.02, but in each interval it is lying somewhere between minus 90, minus 80 to plus 120. So, they are more or less uniformly distributed across the entire range, whereas the Gaussian random numbers, see how nicely they are peaked at that midpoint and with a standard deviation 1. So, this is how you will generate random numbers using these two functions and subroutines. These uniform random numbers are required in Monte Carlo simulations, and Gaussian random numbers are needed when you want to assign all the velocities of the particles in a gas. You know that molecules in a gas are distributed according to the Maxwell-Boltzmann distribution of velocities. So, one way to get the Maxwell-Boltzmann distribution of velocities is through your Gaussian random numbers. So, now we will move to numerical integration. So, we will do briefly numerical integration and differential equations. Just a very simple two algorithms for numerical integration and two algorithms for differential equation. So, what is numerical integration? Numerical integration is, I have a set of data. My data is x0 f x0, x1 f x1, xn f x1, that is like xi yi. I have set of data xi yi and I want to integrate the function x numerically, because I do not know the formula. So, I want to numerically integrate that. So, how do I do that? This integral x0 to x1 f x dx. So, this is my integral. So, I split that integral into n segments. So, there are n segments. In each segment I integrate xi to xi plus 1. Okay. So, this is my integral which is split into n segments. So, one way to split the segment is to use what is called a trapezoidal rule. What is a trapezoidal rule? This is my fxi, this is my fxi plus 1. I assume that the function varies linearly between these 2 points. the function varies linearly between these 2 points. So, I vary linearly, the function is a linear function. So, what is a linear function? My linear polynomial f x I plus delta f x I by h x minus x I for all x I going from x I to x I plus 1. Okay. So, delta f x I is the difference between f x I plus 1 and f x I. So, when I integrate this is the first order polynomial. When I integrate this function, this is what I get is f x I into h plus f x h I by h into h square by 2. So, this is my integral h by 2 f x I plus 1 plus f x I. So, this is really the area of this trapezoid. What is the area of this trapezoid? f x I plus 1 minus f x I, take the difference, take the average value is this point, and that average value you divide by this interval, that interval I have called h. So, area of the interval is half of the height between these two multiplied by the base width. Okay. So, that is my integral. So, since I have n such intervals, my total integral will be h into f x naught by 2 and h into f x n by 2, and all the intermediate points they have to be multiplied by h, because the first point is only h by 2 times f x naught, last point is h by 2 into f x n. All the intermediate points will come twice, one from the left side, one from the right side. So, h into all the values of the function. So, now it is very easy to program it. How will I program it? Read all the data. Okay. So, read all the data, okay. Sum from 1 to n minus 1, sum the values of x I and multiply by h. So, that is one term. The first term and the last term, you add the two terms, okay, divide by 2 and multiply by h. So, this integral is a sum of quantities. What are those quantities? All the functions added from 1 to n minus 1 multiply by h, and the first one and the last one add the 2 and multiply by h by 2. That sum is the integral using the trapezoidal rule. So, I will conclude at this point, and in the next hour I will consider Simpson's rule and also how to solve differential equations. I will consider briefly and then do the detailed programming for the same. So, I will conclude this one here. Thank you.